Okay, let's go to ordinary current AC. This is chapter 31, and in this case we're dealing with a element like current and voltage, right, that oscillate. We know already that when we have a coil rotating inside of a magnetic field, an electromotive force is induced. And we found this equation, electromotive force equals to amplitude times sine omega t. Of course, this is a simple harmonic motion. We have charges that oscillate, they move back and forth, so that produces a simple harmonic motion, correct? And the quantities that are changing is going to be the current and the voltage. They change also, well, it's going to be, right, the power too. Great. Now, to study these two quantities, current and voltage in AC circuit, we use the phasor diagram. A phasor diagram is just these two quantities, current and voltage, represented by an arrow that rotates counterclockwise with some frequency omega, correct? And the projection of these magnitudes onto the x-axis are the instantaneous values. For example, this is the maximum voltage, this is the instantaneous values, right, for voltage. This is the maximum current, the instantaneous current, right, the projection onto the x-axis. Perfect. So as we know, when we have a quantity that changes, right, or have a simple harmonic motion, we can represent it in this way, like in this picture, right? This is the electromotive force induced, and this is one instant. In this case, right, we have that the component in the y direction is in function of sine, in the x direction in function of cosine. In this analysis, we use voltage, right? Voltage equals to the maximum times cosine omega t, right? Which is this equation right here. Perfect. In this chapter, we are dealing with AC circuit, and we are gonna work with current only, capacitors only, and inductors only. And later, we have to combine, right, all of them in series, right? And this analysis goes in finding the relationship between voltage and current for each case, using, of course, the phasor diagram to study the phase, right, the difference in phase between them. Perfect. Also, let's find the average power for each case. Perfect. Now, let's go to, again, R only. Okay, the resistor only. For a resistor only, we have that this is the source, right? This is the resistor right here. And this is the current, this instantaneous current, and this instantaneous voltage. We know, right, that this is the initial one, this is the instantaneous voltage. What about the instantaneous current? Well, instantaneous current using Ohm's law, right, this Ohm's law right here, is equals to the instantaneous voltage divided by the resistance. But the instantaneous voltage equals to the maximum voltage times cosine omega t divided by R, right? And again, using Ohm's law, this quantity is the maximum current. So current then is equals to maximum current times cosine omega t. Perfect, which is this equation right here. Correct. Now, let's see. We found the relationship between these two. As you can see, these two quantities are in phase. What should be then the phasor diagram? Well, the phasor diagram for this circuit isn't only a resistance, it's gonna be in this way, correct? So this is gonna be the current, is gonna be the voltage, for example, current and voltage. And this is the instantaneous current, and this is the instantaneous voltage. Again, this rotates in this direction counterclockwise at some frequency omega, right? And of course, these two are in phase, and we can represent them also in this way, right? If this is one quantity, correct, this is the other quantity, correct? They are in phase. Oops, they are in phase like this. Okay, imagine this is voltage and this is current. Now let's find the average power, right? Well, for each one, what is the average for the current right, using this function where the average for the current, right, is equals to 0, and the average voltage, right, average voltage also 0. Usually every time we have a quantity that oscillates right back and forth, the average is 0. But what about the power? Let's find the power for only a resistor. Well, in this case, power is the instantaneous power is equal to the instantaneous voltage times the instantaneous current. And we know that the instantaneous quantities are right here. It's gonna be voltage times cosine omega t times current cosine omega t. Perfect. And this equals to voltage current cosine square omega t. Now let's find the average. Let's find the average. Well, in this case, the average power is equals to current times voltage times cosine square omega t average. And it's found that the average of cosine square, the average of this cosine square is 1/2. Means then that's equals to voltage current divided by 2, or equals to voltage divided by square root 2 times current divided by square root 2. Correct? Now let's do the same steps using current, for instance. Okay, let's go for current. So this is current equals to maximum cosine omega t. Let's take the square, okay, the square, and let's square both sides. And then what do we have? Well, this is equals to current square times cosine square omega t. Now let's take the average. Again, this is a square. This is the square right here. Now let's take the average. Average of these two quantities or sides. Okay, well, the average of this part is equals to, this stays the same because it's constant, correct? But this one, the average we found it before, is equals to 1/2. It's equals to current square divided by 2. Now, let's take the square root. Both sides, right? Square root. Okay, now when we take the square root, this quantity take a special name. This is average. Now let's take the square root and the square root right here, right? And this is called the root mean square current. So now be root mean square current. Now it's equals to, is defining the square root of this quantity square average, and this is equals to current divided by square root 2, which is the same as this quantity right here, but this is actually right the average power. And the same thing happens to the voltage because they have the same function cosine, right? We'll find also that the root mean square voltage is equals to the maximum divided by square root 2. But this is also the same as this one, which is related to the average power. So the average power can be represented also in this way. Is equals to the root mean square voltage times the root mean square current. Correct? Perfect. Now what about, well, with this we finish the AC circuit using current only. Let's go to capacitor only. Yes, capacitor only. Imagine that this is this circuit. So we have the source and we have the capacitor. Correct? This is the capacitance. In this case, we are dealing with this equation. Using this equation, we have that the charge is equals to a capacitor times the instantaneous voltage to the capacitor. But this charge is related to current. Remember, instantaneous current is equals to the change in charge respect to time. Also, we found it's equals to maximum current times cosine omega t. Correct? Now, because we're looking for this charge right here, let's solve for this quantity then is equals to the maximum cosine omega t times dt. Now let's integrate both sides. And this is charge equals to maximum current divided by omega times sine omega t. Correct? Perfect. Now let's substitute this value right here. And what do we have? We have that current over omega, correct, times sine omega t must be equals to C times the voltage to the capacitor. From here we solve for this voltage to the capacitor is equals to current over omega c times sine omega t. Great. And this is again the voltage to the capacitor. It's gonna be current. By the way, yeah, we can use that one. Current divided by omega c sine omega t. Perfect. Now, also we can represent this in this way. This is equals to current over omega c times cosine omega t minus pi divided by 2. And in this case, we can see that voltage through the capacitor is out of phase respect to the current, right? What is the difference? Pi divided by 2. Pi divided by 2. And we represent this in this way using the phasor diagram. If this is the maximum through the maximum voltage to the capacitor, this is gonna be the current. Correct? Remember the phasor diagram rotates counterclockwise, correct? So we have a difference in phase of 90 degrees. Means that the voltage to the capacitor is behind the current by 90 degrees. Correct? Perfect. Also, look, let's work with the maximum quantities. We found that this is the voltage to the capacitor. What should be the maximum voltage? Well, the maximum voltage is when this quantity is 1. Correct? If that quantity is 1, what do we have? Well, we have that the maximum voltage or amplitude is equals to current divided by omega c. But when we compare this to Ohm's law, what do we have? Well, we can represent this in this way. The maximum voltage to the capacitor is equals to current times a quantity that represents the resistance, and this is called the capacitive reactance, correct? And this capacitive reactance is equals to 1 over omega c. Right. So we found again this equation using maximums, right? Or amplitude is equals to the current times this capacitive reactance. Or the reactance of the capacitor. Correct? And this is equals to 1 over omega c. Correct? Of course, the units for this reactant is the same as for the resistor ohms. Okay, perfect. Now let's go to the next circuit, which is using just a inductor. Okay, let's go for the inductor. Correct, the same step. Now this is the inductor, and we are looking for the current or the relationship between current and voltage. Also, we're looking, remember, for the average power. The average power for the capacitor is gonna be 0. Okay, average power for the capacitor is 0. Because we have the product of sine and cosine. Sine and cosine, well, the average is gonna be 0. Remember when we have on the resistor, we found that it was cosine squared. The average of cosine squared is 1/2. And the average for sine and the average for cosine are 0. Perfect. Now let's go again to the inductor. Wait. For the inductor, we use the voltage through the voltage drop through the inductor is equals to the inductance times this change. Okay, so let's do it. So the instantaneous voltage is equals to L, right? Changing with respect to time. But what is the current? They was found the current to be current times cosine omega t. So it's equals to then L times the derivative of maximum, right, cosine omega t respect to time. And what is this derivative? It's gonna be L times current, correct, times negative sine omega t, right, times omega. Correct. So this equals to negative current L omega, correct, sine omega t. Also, we can represent this in this way. This is equals to negative. This is equals to, because remember, cosine omega t plus pi divided by 2 is equals to negative sine omega t. If we use this relationship, we can get this equation gonna be equals to current omega L, right, cosine omega t plus pi divided by 2. Correct? So again, we found this quantity, right? The voltage to the inductor is equals to, we can use this equation or this equation. Okay, gonna be current omega L sine omega t, or we can use this equation, right? Well, when we compare this voltage to the capacitor to the current to the inductor, to the current to the inductors, we can see that these two are out of phase, right? And what is the difference? Pi divided by 2. What should be the phase diagram or the phasor diagram? The phasor diagram now is going to be in this way. It's going to be current, this is going to be voltage to the inductor. What is the difference? It's going to be 90 degrees. In this case, the voltage through the inductor leads the current by 90 degrees. Okay, perfect. Now let's continue. Let's find the maximum quantities, correct? The maximum, we'll use positive values right here, and again, this function is 1. That's the maximum for sine. And what do we have then? We have the maximum voltage to the inductor is equals to current times omega L. Again, when we compare this to Ohm's law, what do we have? Well, that we can represent this in this way. Current times a quantity that represents this product, right? And we call this the inductive reactance, correct? The inductive reactance is defined to be equals to omega times L, right? Inductive reactance. Perfect. And then we have these quantities. We have this maximum voltage to the resistor, to the inductor is equals to a current times this reactance, where this reactant is equals to omega times L. Correct? Perfect. Now let's write the conclusion for these three elements. For these three elements that we found so far, correct? And we found, for example, the element, right? Also we have the amplitude, correct? We have the amplitude. Also we have the quantity, and we have the phase, right, of the voltage. Correct? Great. And well, these are the elements, are the resistor, we have the capacitor, and we have the inductor. Let's write the names. It's better, correct? We have the resistor, we have the capacitor, and we have the inductor. For example, it's gonna be, right, R, that's the amplitude. For capacitor, we're looking for VC, and for the inductor, VL, right? And that'll be current times the reactant. This is current times the reactance of the inductor. Where these quantities, right? This is equals to well, it's the same thing. Gonna be the voltage to the resistance equals to current times resistance. Correct. The quantities are this quantity of the reactance is equals to 1 over omega C, right? And the reactance through the inductor is omega L. Okay, the relationship between voltage and the current when we're dealing with resistor, capacitor, inductor. Well, this is in phase, right, with current. For the capacitor, the voltage lags, right? Lags current by 90 degrees, correct? Lags current by 90 degrees. And for the other one, the last one, voltage leads, right? Current by 90 degrees. Correct? And we represent all of them in this way. This is also maximum, right, for the inductor, maximum for the conductor, and that's the current. Remember, it's a motion counterclockwise. And in this case, one more time, the voltage to the capacitor is behind the current by 90 degrees. And the voltage to the inductor is ahead, right, or leading the current by, again, 90 degrees. Correct. Great. And with this, we finish the analysis for these three elements. In the next video, we are going for the combination of these three elements and do the same thing. Let's find the relationship between voltage and current and find also the average power. Right here, the average power for the inductor is also 0 because the same thing as before, this voltage to the inductor is sine, the same thing as for the capacitor, right? But for the current is gonna be cosine. When we are looking for the average, when we make the product, the average for these quantities, right, is gonna be 0. Great. See you then in the next video. Bye.